Where will the meeting?
We want to do something real in an abstract
Wait,
way.
so the problem just have the board, is it like relating to the paper you just gave us?
Yes.
Okay, should
Yes.
we take notes?
Okay, so this is, yeah,
I would.
and I'm officially recording this too.
Somebody have a pencil?
Okay, so this optimization is huge, people.
Oh my god, that was you start.
Yeah. Okay, so optimization is where we're gonna take some interesting quantity that we have a need to optimize, meaning maximize or minimize, depending on the circumstances. And we're going to use calculus to do that. So for example, let's say we're manufacturing an open box. It's to have a square base and a surface area of 108 square inches, okay? We want to design this box so as to maximize the volume, given those parameters, okay? And this is the kind of stuff that you really do in life, right? You really do want to do things like, given some constraints, let's maximize something, get the most bang for our buck, right? So, okay, so to do this then, we're gonna go ahead and we're gonna kind of follow our process here. Here's our process for optimization. So we need to assign symbols to the variables that are given, or maybe maybe they're just some implied variables, right? And we need to figure out what those are. So define our variables, in other words, and make a sketch when feasible. Well, there's our sketch, and the variables are actually given to us here. Right, we're saying that the dimensions of the square base we'll call x, right? It's an x by x square base, and the height we're going to call h, right? So in terms of those, that's step one. Okay, all that stuff is summarized in the picture there. Step two is big. Step two is we want to come up with the primary equation, and the primary equation will always represent the quantity being optimized. That's always where we start. So what is it that we're trying to minimize or maximize here?
Volume.
Volume. Okay, so then that means that step two means that we're going to write V equals, and we're going to come up with an equation for volume.
HX squared.
So it's just going to be the area of the base times the height, right? Does that make sense? Just a rectangular prism. So there you go. Okay. We've got a little bit of a problem here. Not necessarily a problem, but a challenge. Our goal here is for us to be able to do calculus on this primary equation. We need to have it as a function of a single variable, because really, that's what this class should be called, calculus of a single variable. We don't ever really deal with how to do the stuff that we do for multiple independent variables. You'll do that in college. It's not a big deal. But even then, we would always prefer, when we're doing calculus, to limit the number of independent variables as much as possible. And so even in the future, we'll still want to rewrite this as a function of a single variable, okay? So because we have two independent variables here, or two input variables, x and h, that means we do need to move on to step 3 and do something. Step 3 is we need to reduce this to a function of a single variable, right? And so that means we're going to require a secondary equation, which I oftentimes like to call an equation of constraint, because it's going to be the thing that is limiting us is always going to give birth to the secondary equation, right? So what is the limit here? And typically you look for a number. There's going to be some kind of a numerical limit almost always imposed on this. In some way it'll be numerical. Surface area. So the surface area, yeah, that is the limiting factor here, right? The surface area is limited to be 108 square inches, right? If the surface area were not limited, this would be a ridiculous question. The answer would just be make it infinite, right? But it is limited. So that means we're going to move on to step 3. And I guess I should label this. So this is our primary equation Now step 3 is gonna be our secondary. Or sometimes we're gonna call this equation of constraint. Okay, so that's gonna be the surface area equation, right? So surface area is equal to 108. Well, what is the surface area of this open box?
6xh.
No.
5xh, because there's one face missing.
No. So, I mean, you're overgeneralizing here, right? The lateral faces are gonna have different areas than the base, aren't they?
Oh, yeah,
Right.
so for xh plus x squared. What would be 5?
Equals 108. Okay, so there's our equation of constraint, right? Now here's where we have to be non-mechanical. We have to look at this and be, smart about this. Calculus is, it's not, I mean, there's an art to calculus, to doing it well. I mean, it's a real, you gotta think strategically. So we have to think now in terms of what is the variable that we want to pick for our substitution variable. In other words, for which variable would we like to substitute in our primary equation, right? And so you have to think in terms of both of these two equations, what's gonna make the most sense. So what do you think? What variable do you think we'll want to substitute for? H would make sense. H would make sense, but why? What are some factors that go into your decision here?
You don't have to square everything.
Okay,
Put it back
yeah,
in.
for one thing, x is being squared in this equation, and so if we were to input for x, we'd have to square that quantity, right? We'd prefer to avoid that. That's gonna mess things up a little.
Aren't you gonna have to root it later?
Say it again?
Aren't you gonna have to square root it later?
I mean, maybe not.
Okay.
Okay, good. Notice that there's only one h here and here, but x appears in multiple places here, right? So solving for x in terms of h would be, that's difficult, right? It's quadratic in x. That's gonna be a little tough, isn't it? If I wanna solve this for x in terms of h, that's a quadratic equation. I should expect to get two solutions for that. I'd probably have to distinguish between solutions that make sense physically and, I mean, I'm inheriting some problems with that, right? So clearly, because the h only shows up once here and there, that makes sense, doesn't it? To isolate the h and make that our substitution equation. Okay, so if we do that, what do I end up with if I solve for h here?
108 minus x squared divided by 4x.
Good. Good, let's put a box around that, because that's our substitution equation. So we're likely to come back to that, but it's important. We want to draw our attention to that. It's an important part of our work, right? And so now, what do you think the end of step 3 is? Plugging it in. Right, so we're gonna take this value of h and plug it in there, and we're gonna come up then with a reduced primary equation. Primary equation as a function of a single variable, right? So now, what do we end up with? If we go back to our primary equation, we end up with v of, what variable are we gonna be left with? X. And I'm gonna write it that way, v of x, okay, is equal to x squared times that, right?
Would we want to just put 108 x squared minus x before?
We can. I mean, we can do, now we'll talk about here in a second about how we wanna probably write that in a way that's gonna make the calculus the easiest, right? But something else we wanna do. We want to define what the domain is going to be in terms of that variable. So what values of x, and we have to think about this, there's two parts to this. There's gonna be the mathematical domain, but then this is a real world problem. And so we have to potentially restrict our mathematical domain to only include values that make sense in the real world problem that we're dealing with, right? It's a geometrical problem. So,
We want to do 0 to infinity.
okay, so possibly, right? So then the smallest value, the lower limit for x would be 0, right? Does that make sense? The lower limit for x would be 0. Now, does 0 itself actually make sense? Well, not really, probably, right? And this is a matter of some debate. Do you include 0 or not, right? I would say, you know, just to make life easy on yourself, there's no sense, right? Think about this like a cartoon, and this is helpful to like kind of make this thing, morph this in your mind. You're good at this because you've actually seen stuff like this. You know, you've probably messed with things that do stuff like this, where when you tweak one thing, something else changes. If I were to tweak this shape so x approached 0 and the surface area is fixed, what would happen to h? So I've got this special material.
Oh, so it approach infinity.
Yeah, h is going to get big, isn't it, right? If the base gets small, this shape gets tall, right? And so at some point, as x approaches 0, h would approach infinity, right? That's clearly not going to be probably a really good thing to have happen, though, right? The overall volume is just going to end up going to 0 there, isn't it? So whether you include it or not, that's kind of up to you. But your domain, so you could either write it as an open bracket or a closed bracket. I don't care. Either one of them would be fine, right? But 0 is our lower limit, okay? So then what's the upper limit going to be? Now we got to think about this in terms of the relationship between x and h. Okay, as x gets big, what would happen to h? H would get small, wouldn't it? So we could look up here and say, okay, as h approaches 0, what does that mean x is going to have to do to make that happen?
It's gonna have to be just root of 108.
Yeah, everybody see that? So x actually cannot approach infinity. It can't, because of this constraint, because of this 108 constraint, right? In order for h to go to 0, that means that the numerator would have to go to 0, right? So there is an upper limit for h, or for x, right? The upper limit for x would be when x squared equals 108, and so x equals the square root of 108, right? And that seems to be a hard limit, right?
Why would it include that?
Well, what if it did include that? If it did include that, that would be where h went to 0, right?
Well, so it's possible to include it just like with the 0.
So it's-
but why would you, that seems like an inconsistency.
Well, okay, so I would argue that 0 you absolutely can't do. If x goes to 0, this thing ceases to have physical meaning, right? Because now it's actually
But
not.
if x goes to root 108, then h goes to 0.
Okay, so what would that look like in terms of the box?
Then it'd be infinitely
It'll be completely
flat.
It'd be completely flat. It wouldn't have any sides on it, right? So that's a calculable volume, though. That's going to give us 0 volume, isn't it? Right? But it's something we could actually make with a piece of cardboard, right?
But it'd be infinitely wide.
No, it wouldn't. No, it'd be that wide. It'd be the square root of 108 wide. Because then all 108 square inches of cardboard would just be the base. You see the difference? Whereas if I tried to do this, I can't build it. I can't build a box that has no width but infinite height. That would be a mathematical abstraction, right? That's equivalent to, you know, a line, for example. And a line doesn't exist in three-dimensional space. You see what I'm saying? You couldn't build that. There's no way you could ever build that shape, but I could build that shape pretty easily, right?
That makes sense.
So to me, by my way of thinking, this is the domain that makes the most sense to me, because this is physically impossible, but that is not. As you do more of these problems, you're going to realize that doesn't matter, because neither one of these shapes is going to give me any volume, right? And so somewhere in between, the answer is going to lie. So do you include those ridiculous, you know, limits of the domain, those endpoints of the domain, or not? I mean, it's not. It's, you know, it's just kind of really becomes sort of a theoretical argument, you know. But that's how I would do it. And then you now know my reasons for doing it that way. Okay. But when I grade the test, which is open-ended, I don't care if that's open or closed. Okay? Not answering. Okay, so there's our function. Now we're to the point where we get to do calculus, right? We've distilled this physical situation down to a math problem, and now we can switch into calculus mode and do what we do.
Just
Right.
take the first derivative, find the maximum.
Right, and so yeah, we'll do the stuff that we did, that you guys are gonna do an assignment to kind of summarize everything we've done from section 3.6, which really just leads up to optimization, right? So you're just good at making a table and using the table to do that, right? Okay, so if we are gonna do some calculus on this, what's gonna make the most sense? To me, I would say split it up into separate terms, so you don't have to deal with a quotient or a product, right? So let's rewrite this as v of x. If I distribute the x squared, what's my first term gonna be? 108x squared over 4x is what? What does that work out to be? 27x?
Yeah.
Minus x cubed over 4? Right? Everybody agree? So this is pretty easy to differentiate, right? So we might as well calculate it v prime. So what's v prime?
27.
Minus 3 x squared.
Okay? And this is easy to calculate a second derivative. So do it, right? It's not a hard derivative. We'd rather use the second derivative test than the first derivative test if it's convenient. What do we get?
Negative 6x. So, negative 3x over 2.
Okay, good. So let's make our table, right?
So this is the 4. What do we do?
This is 5. 4 was in the
So on the little steps here then, yeah, so step 4 was the domain. I just lumped that with step 3. Right? I came up with a domain that made sense. And now you can kind of see why that domain is important, because it limits where we have to look for critical numbers. So we went from 0 up to, what was our upper limit? Square root of 108?
Weird.
Oh.
Ghosted.
There we go. Up to square root of 108. And let's find our critical numbers. So if we look at the first derivative, there's gonna be, nowhere is it undefined, right? So we're just gonna solve this, find the zeros. So to find the zeros of our first derivative, that's just gonna be when x squared equals 4/3 times 27, so 36, right? We're gonna set that equal to 0, right? Everybody agree? So that's gonna be when x equals plus or minus 6.
Wouldn't it just be positive?
But just positive, because that's the only one that falls in our domain, right? So we get 6 is a 0, and then do we need critical numbers of the second derivative?
Oh, we just get signs.
We don't need a critical number. We're not looking for inflection points. We're looking for a maximum, right? So we just need sign. So what's the sign? Well, look at the second derivative. For any non-negative value, or for any positive value of x, second derivative is negative, isn't it? Right? So that's negative, which makes this a horizontal tangent line and downward concavity. So it's our maximum, right? And we solve the problem. What's it really asking for? It wants dimensions, I think, right?
Yeah.
So we know what x is. X is 6. So where do we go to find H?
We're gonna make this six squared.
Box equation right there, right? So if X is 6, then H would be what? So H is going to be 108 minus 36 over 24. What is that? 72 over, so 3. Right, so our dimensions are just 6 by 6 by 3. And that is the volume, that maximizes volume. Those are the dimensions, the only configuration that's gonna give you the biggest volume. That's pretty cool.
Wait, why isn't every volume the same? Like, if it's.
You use the principle of exaggeration, right? The principle of exaggeration is a great tool. So what if we took a volume where X was almost the square root of 108 and Y was just really tiny, right? That's gonna be a small volume, right? I could take a single drop and spread it out over, right, over the base so it had some height, and that's not very much volume, is it?
So it's the absolute maximum, has the absolute, it has the maximum volume.
Yeah. It has a maximum volume, yeah.
So what if there was more than one possible X?
Then we'd have to test, if there's more than one critical number, then we'd have to test them and
Just
see.
plug the X value into the function, so if your Y value is higher.
Is that a coincidence that the volume and surface area are the same in this problem?
Yes,
Okay.
You point out a lot.
I mean, it's kind of a coincidence. No, it's a good point. It's kind of a coincidence, but it will, I mean, it's, in general, it's always gonna work that way for a square-based open box. I mean, it's sort of a coincidence, but this is kind of a symmetrical shape too.
There's a lot of coincidences
I
in
don't wanna
life, right, Braden?
Okay, let's try another one.
This isn't real.
Okay, let's do, here's a good one. This is,
Try. Don't listen to me, Braden, I'm crazy. That's what's crazy. Just people trying to learn other people from the real world. Sounds like something your face would say.
What is he just backwards?
Wow, there's biology too, so.
okay, how about that one? So what if we wanna find the point on the function y equals 4 minus x squared closest to the point 0, 2? So it'd be like sliding a bead along this function. We wanna locate the bead where it'll be closest to that point. Okay? So in this case, the variables are just x and y, aren't they?
Would we just be able to graph it and then like hold a string up to it?
That's how we wanna do it for sure.
Yeah, just use Desmos.
So what's our primary equation gonna be then?
Y equals 4
So what's equals T
Or
minus
do you have to
y?
find
Well, I mean, if we wanna come up with, I mean, we're talking about a distance, right?
Oh, so we have to do the Y minus Y1
Yeah.
equals X
Yeah.
times X.
So here's the equation that relates x and y, right? But we're really looking for a distance, right? And so our distance, how might I write our distance function out?
Just
So d squared, how about, right? Distance squared
equals X squared plus Y squared.
equals x squared, well,
It's just the Pythagorean theorem.
it's gonna equal the difference in the x values squared plus the difference in the y values squared, right? I mean, if we drew a picture, all this really is gonna be, if we draw a picture, this is just an upside down parabola with a vertex at 0, 4, right? So it's gonna look like that, right? and this is the 0.02 right there.
Oh, that is kind of interesting.
Okay. And so if I just pick some random point here that we're gonna call x, y, right, then this is just a Pythagorean triangle, right? Where this is D, and that's what we might call delta x, and that's what we might call delta y, right? Everybody agree? So D squared is just gonna be the quantity x minus 0 squared plus the quantity y minus 2 squared, right? Agreed? Okay. So if we're trying to minimize distance, then do I need to solve that for D and take a square root of both sides? Well, let's think about this. If we want to minimize distance, isn't that the same thing as saying let's minimize the square of distance? Won't the square of distance, won't that quantity be at a minimum when the actual distance is minimum also? You see my point? Think about that for a second, right? Isn't it a much easier function to deal with the square of distance than distance itself? Because distance is going to involve a radical, right? That makes the calculus harder, right? So we want to be smart about this. We want to say, okay, well, fine. We could actually find the distance if we want to, but let's do the calculus for a problem that's going to give us the same answer, but it's easier to deal with, right? Okay, to be continued.
I like this optimization stuff.
Yeah, it's cool, isn't it?